Well, friends, welcome. As you can see, we have this very question that was given by one of my students who was trying to solve this question for some time and they was struggling it. So right now, as we have it in our disposal, we have to try as much as possible to break it down. Okay, so as we can see, without any limits, okay, without our limitation right now is the XY, as you know, a lot of people will fumble with. Okay, so let's see something. Um, without the introduction of the variable y, as I've written over here, the introduction would have been easy to manage. Okay, so without wasting time, let's see how best we can break it down for everybody to be happy. All right. Okay, so okay now, so the question, as we can see, is given as 1 over 1 plus x y 1 plus xy into bracket square roots of 1 minus x squared dx. That's the integral that we're supposed to manage. But if you look at the integral very carefully, we will see that the xy was the reason why, you know, we found it very difficult solving the xy over here. So tonight we are going to take our time to break it step by step. Before we start, we know that we can make an assumption that let's substitute x to be equal to sine of theta. If we say that, we see our limit, the limit was given was 0 and 1. Okay, 0 and 1. So when we differentiate this, we are going to get dx sine theta d theta. Okay, so if that is the case, then our limit is going to change. Why is it going to change? It's going to change because when x is equals to 1, the answer we get will be sine theta to be equals to 1. So therefore, theta is sine inverse of 1, which we all know, okay, is pi on 2. If 1x is equal to 0, sine theta will be equal to 0. Therefore, our theta will be equal to sine inverse of 0, and we all know is 0. So the limit has changed. As you can see, the limit has changed. Okay, that's our limit. Now, we made assumption that x is supposed to be equal to sine theta. So because of that, if that is the case, when we substitute this, back into our expression term, then our integration is going to be integral pi on 2 0 1 over 1 plus y sine theta into bracket 1 minus sine square theta d theta. Okay, so this is what we are able to do so far because of our substitution. also bear in mind that if we have sine of 1 minus sine square theta over here, this we can write it as square root of cos square theta. Okay, cos square theta. Look at it very carefully. Okay, so we know, that when we differentiate sine, yeah, look at it. When we differentiate sine over here, we get cos theta d theta, not sin theta d theta. So that will be cos theta d theta. Okay, so now over here, when in place of dx, we can replace it with cos theta d theta. Okay, and this because you know the cos square theta. Now the square root of that will also give us cos theta. So when we substitute everything back into the equation, we are going to get integral pi onto 0, 1 all over 1 plus 1 sine theta. Okay, the x is here, so this will cos theta d theta all over this cos theta over here. So our simplification has become so very easy. So this, then we can break it down once again, because then the cos will take care of the cos. So that eventually the equation will be the integral pi onto 0 d theta all over 1 plus y sine theta. Okay, so this is the integration that we have to take care of it. But we are going to make some assumptions. Our assumption, we are going to say that let z to be equal to tan theta over 2 for half angles. Okay, if we say that, then let's square this one. Let's square the expression term. Let's square the expression. So when we do that, then z squared, okay, will be equal to tan squared theta over 2. But we know that tan squared theta over 2, tan squared theta over 2 over 2 is equals to sec squared theta over 2 minus 1. Okay, so if that is the case, then making sec squared theta the subject over here, this will be 1 plus tan squared theta over 2. Okay, so with this, we can substitute z into this equation. So therefore, our expression for sec squared theta over 2 will be equal to 1 plus z squared. Let's put in this equation somewhere, because it's going to be useful somewhere along the line. So this, once again, will be useful to us. Now, when we differentiate z, which is equal to tan theta over 2, okay, we are going to get dz to be equal to half sec squared theta over 2 d theta. Okay, and this when we make d theta the subject, okay, now we can, everything will be in terms of dz. So we, here will be 2 dz, yeah, is equal to half sec squared theta over 2 d theta. So letting the theta standing alone, the whole expression will be d theta will be equals to 2 dz all over half sec square theta over 2. Okay, we know that sec square theta, sec square theta over 2 is equals to 1 over cos square theta over 2. So therefore we can substitute this in here. Then our expression will be 2, okay, will be 2, okay, cos square theta over 2 dz to be equal to d theta. So we can substitute this into our equation, our expression. Okay, so when we do that, we are going to get our expression to be the integral. Well, so let's put this one aside. And so because we use it again, okay, use it again. Now we said dz is equals to sec square theta d theta. Okay, so now we'll be able to get our d theta here. So when we substitute everything into the integral, okay, then our final integral is going to be integral, I'll bring the 2 out, 2 cos squared theta over 2 dz, okay, all over 1 plus 2y sine theta. Okay, but this one we can further break it down. We should remember that if we have sine 2 theta, which is usually given as 2 sine theta cos theta, then when we consider it in terms of half angle, the sine theta will give us 2 sine theta over 2 and cos theta over 2. So if that is the case, we can substitute this in place of the sine over here, so that eventually our integral will be 2 out pi on 2, which we know is to be our limit, pi on 2 over 0 and 0, will give us cos theta over 2 d theta, okay, for dz, the cos, okay, so as you can see, so sine 2 theta give us 2 sine theta cos theta, and the sine theta give us 2 sine theta over 2 and the cos theta over 2. Okay, so upon substitution, we have this. Okay, everything is frozen a bit. What's happened tonight? Okay, So theta over 2, okay, it's lost. We'll get a little bit of connection lost. Bring the connection back. Okay, so as you can see, so all this one over 1 plus 2y, and this one will be 2 sine theta over cos theta. Okay, so you see that our sine theta is now changed. Okay, so we are going to make sine theta the subject of an expression. Okay, so the down one, we are going to get sine theta, okay, with 2 as a time sine theta, okay, once again, sine theta, okay, over 2, and of cos theta over 2. Okay, beautiful. Right. So now let's simplify our integration by cleaning our way to be very, very neat. Okay, so when we pick this, okay, then we have our eraser is back. Okay, so now pick on eraser and we'll clean the DZ. Okay, okay, so now we're back. Now we have DZ. Okay, now so our expression is looking now very, very, very beautiful. So sine theta is 2 sine half over that, so that gives us that. And down there we had y sine theta, not 2y, so y sine theta. Okay, right. So now let's come down here. Having this expression is good, but we can do more. So let's do a bit of factorization over here. So let's factorize. So let's factorize cos theta on 2 out of our integration. Okay, so this, if our integration is like that, the integral pi on 2 0 cos theta over 2 dz, okay, all over 1 plus 2y sine theta over 2 cos theta over 2. So we are going to divide here by, and all this one by cos theta over 2. So we divide that one. This will be cos theta over 2 all over cos theta over 2. When we do that, so we are going to get pi on 2 0 1, which is dz, okay, over 1 cos theta over 2 plus 2y, okay, sine theta over 2 divided by cos theta over 2. So eventually we'll end up having, as we put a 2 out, okay, the 2 comes out, right? Because of the integral from right from the start here, the two supposed to be here because of engine. Good. Our system is slowing down today. So, here, because of the, we omitted the 2, there was a 2 here. So 2 come here, we have, yeah. Alright, so the 2. Then we have the z all over 1 over cos squared theta will give us sec squared theta over 2 plus 2y tan theta. Okay, it's looking very nice. This is how our equation is looking now. Okay, so if that is the case, let's bring it down here and write it well so we don't lose anything. So the final integral is 2 out pi onto 0, pi onto 0. We have the z all over sec square theta over 2 plus 2y tan theta. Okay, if that is the case, we remember that initially we substituted the sec square theta. After we simplify everything, we had sec square theta over 2 to be z squared plus 1, and also we know our tan theta is tan theta over 2 is also z. So if that is the case, we'll do back substitution. Our back substitution will give us integral. You see, when we put those values back, we are going to get 1 and 0. Okay, then also this will be dz all over sec square theta, which is z squared plus 1 plus 2y tan theta, which is z. Okay, so you see we have different expression at the moment, but if we look at it very well by inspection, you see, by inspection, you will see that the integral, the denominator, which we can write it as z squared plus 2zy plus 1, is a polynomial. It's a polynomial. So because of that, we can take our time and look at it. So looking at the denominator, z squared plus 2zy plus 1 is a polynomial, which we can also write it like z squared plus 2zy plus, you see, if you look at it very well, I can say y squared minus y squared, which is 0 plus 1. We haven't changed anything. Okay, so upon further breaking it down, when we factorize very well, we see this can be z plus y all squared, okay, minus y squared plus 1. Okay, well, finally, we can also write this one as z plus y squared. Yeah, then if you look at it very well, plus 1 minus y squared, which is the same, so I haven't changed it. So I can substitute this in place of my final integral. So therefore, the final integral, let me use red, will be the integral dz all over z plus y squared into bracket, yeah, plus 1 minus y squared. Okay, so when you look at this, you know there's something we can do, because you know for sure we can do a certain substitution that can help us. Why don't we say that let xi to be let xi to be equals to x plus our y that we have in our equation. So when we differentiate, the xi will give us z plus y, z plus y, so z plus y, sorry. So z plus y, that's what we have in the denominator. So z plus y. So that we can say this is equal to dz. Okay, if that is the case, then our limit will change. Because over here, when z, since our limit is still 1, 0, when we say z is equal to 1, then our limit will be xi1 equals to 1 plus y. So that will be the upper limit. Then when we say xi equals to z is equal to 0, our xi0 will be 0 plus y, which is still y. So our limits have changed to 1 plus 1 and y. So when we put the limit back into the integral, okay, then the z is no more the z. We are going to get integral the xi all over 1 plus y, and this will be y, all over z plus y squared plus 1 minus y squared. So this has become our integral. So friends, you see that it's becoming easy. If you look at this very well, you see that we can use the tan inverse. Yeah, tan inverse to do that. Bear in mind, we still have our 2 here. Since we factorize it, 2 is still out again. So now our final integral, yeah, when we integrate this, finally, we are going to get 2 out of all. Then we say, if you look at xi over here, the xi over here is equals to that. So instead of z plus z squared plus y, z plus y squared, or this z plus y, this one, I'm cleaning well. So this z plus y squared. This is z plus y. I don't know why I made this one. So for this, z plus y all squared, this is squared, good. So with that, what comes into your mind? Instead of z over here, we can write this integral. Let's write integral here first before we integrate it. So when we clean this one, okay, So finally, our integral. Now, since we want everything to be together, we know that xi is equals to z plus y. So when we substitute back into the equation, then the final integral will be 2 out 1 plus y the xi all over xi squared plus 1 minus y squared into bracket. No, 1 minus 1 squared. Let me see this 1 minus 1 squared. Yeah. So that will be 1 minus y squared. So this, I think when we look at this one, we'll be able to integrate this using a tan inverse function. Tan inverse. So we can use tan. So using tan inverse function, okay, of integration. I can't remember when we have integral of 1 over s squared plus a squared, we can say that 1 over square root of a tan inverse of the x all over square root of a. Yeah, so this, if that is the case, then we can integrate this with this knowledge, yeah, with this knowledge at hand. So let's break it down. So when we integrate using this, then our integration will bring the 2 out. Our limit is still there. So this one will be 1 over square root of 1 minus y squared with a tan inverse of xi all over square root of 1 minus y squared, okay, with our limit 1 plus 1 plus y and y. Friends, I think when we substitute the limits into the expression, we should be able to integrate this with ease. Now that we have all the integration has been done for us, you see. So this is 1 plus y. Okay. So when we put in the upper limit, which is y plus 1, we are going to get so 2 out. Okay. So 1 plus y means 1 over square root 1 minus y squared tan inverse of 1 plus y over, okay, square root of 1 minus y squared. This is our upper limit minus the lower limit, which will be the same 1 out square root of 1 minus y squared, okay, tan inverse of y all over square root of 1 minus y squared. Okay, so this will subtract from that, and that will give us our final answer. So let me write it well, since we are bulging out of the blackboard. So this, okay, so this will be 2 out 1 over square root of 1 minus y squared tan inverse of 1 plus y square root of 1 minus y squared into bracket minus, okay, this, which is 1 over square root of 1 minus y squared, tan inverse of y over square root 1 minus y squared all together. So when we simplify this gives us a final answer. If you look at it very carefully, you see that there's a common one out. So we can bring this one out to be 2 over square root of 1 minus y squared out. Then the rest will be tan inverse of 1 plus y all over square roots of 1 minus y squared, okay, minus tan inverse of y all over square root of 1 minus y squared. And so this will be the integral. Well, friends, it's getting longer and longer. And since we are able to break the back of the horn, okay, I will leave it with you to finally deal with the one in the middle. If you do it very well, you should get something like cos inverse of y all over 1 minus y squared. Well, it's been long, so let's recap. Let's go up there and see what we did from the scratch. So all what we did was integration. The integration was given to us, okay, and all what we did was, substituting the integral to be y. Okay, so we say let x to be equal to sine theta, and when we differentiate the sine theta, we have cos theta d theta. Okay, so this is a substituent that we're going to use to replace the dx over here. Okay, now when we did that, meaning the values of the intervals will change. So when we substitute x equals to 0 and x equals to 1, we had pi on 2 and 0. So pi on 2 and 0 come here. And also we did our final substitution over here. Okay, then we know that as we said x to be equal to sine theta, we have 1 plus y sine theta. Okay, then here we know for sure that when we put in the x over here, yeah, we have our 1 minus sine squared theta. Okay, 1 minus sine squared theta here. Okay, 1 minus sine squared theta, which we also know that when we place cos squared theta in, we have everything in, we're going to get cos theta. So we substituted the respective variables into the equation, and eventually we ended up with this. All right, now we made an assumption saying let z is equal to tan theta over 2. Then we squared, and we have z squared is equal to tan squared theta over 2. Then tan squared theta over 2 is z squared theta minus 1. Then we made z squared theta the subject. Okay, then we had z squared theta. Let's write it as z squared theta, which is z squared theta. Then that gives us 1 plus z squared theta. Okay, after that, we differentiated the z, which we assumed it to be tan theta over 2. Then we had dz to be equal to 2 dz over half sec squared theta. Also, our assumption was sec squared theta over 2 is 1 over cos squared theta. So when we simplify everything, we ended up with this. Okay, we ended up with this. Then we substituted it back into the integral. Then this one we had 1 plus y sine theta and that. Now we also know that sine 2 theta is for double angle is 2 sine theta cos theta. And also because of that, when we consider half angle, our sine theta will be 2 sine theta cos theta over 2. So we substituted that into this equation, and after that we have this expression. Okay, then we factorize cos theta over 2 out. Then we ended up with dz over sec squared theta over 2 plus 2y tan theta. Okay, then since we know that let's come back here. Since we know that sec squared theta is equal to z squared plus 1, and also this I'm talking about, and also tan theta over 2 is equal to z. We did back substitution into the equation. Then we realized that the denominator here is more of polynomial. Then we did a bit of expansion over here. Okay, but when we factorize everything out, and we have z plus y squared, 1 minus y squared, and we substituted into the integration. Okay, knowing that xi is z plus y, we substituted back, and we have final expression like this. That looks more like what's the name? That looks more like a inverse tan function. Now we have 1 plus y and y as a limit because the z values of the limits, upper limit and lower limit, have changed. So we put a z value for the upper limit into the xi substitution with it. We had 1 plus y, and z being equal to 0. Our xi substitution once again became y. So finally, when we substituted, we have this expression. Okay, that expression that was of high interest because then it helped us to be able to integrate it. Okay, now also here we know z plus y squared is xi. Okay, so we put a xi into the integral, and we use the inverse integral function, which says 1 integral of 1 over s squared plus a squared is given as this. Then we use the same approach, then eventually we got to where we are right now. Friends, I will leave you guys here. Please subscribe and ring the bell so that that will help us to be able to get in touch and do more. Have a good evening and see you around.